So here we're going to find the work done by this vector field as an object moves between these 2 points. So we're going to start by seeing if the vector field's conservative, by seeing if there exists a potential function, where if we take the gradient of that potential function, we get this vector field back. And that's because if this field is conservative, then when we try to calculate the work done, and C is actually any path between these 2 points, we'll notice we can replace our vector field capital F with the gradient of the potential function. And this is great because if you notice, if it's in this form, we get to use the fundamental theorem of line integrals, which tells us that this line integral will just be the potential at our end point minus our potential at our starting point. So our first step is going to be to see whether or not a potential function little f actually exists. If one exists, then we know our vector field's conservative. If one does not exist, then we know our vector field is not conservative, and we would actually need more info to be able to do this problem, because in that case, the work would depend on the exact path. As an aside, if you'd like to see a more formal way to determine if your vector field's conservative, you can also test if the curl of f is 0. And we're going to get to this at the end of the quarter, but if you'd like to see how to do that, I'll do that on the last slide, and I'll show you how to find the curl and see if it's 0. But it's just as effective to jump right in and actually just try to find your potential function, which is what we'll do here. Okay, so I want to find my potential function which means that the gradient of my little f has to give me my vector field back, i.e., okay, so really I have 3 equations that have to be satisfied here. So let's do method 1, the merge method that I talked about in class. And if we do it this way, we're going to really just write the 3 equations that have to be satisfied. So I know my I components have to be equal, which gives me this. My J components have to be equal. And so that means that, let's look at the top equation. If I integrate both sides with respect to x, holding both y and z constant, that means that f is going to have to be y squared times x plus any function of y and z, because I'm thinking of those as a constant. Okay, so that's any function of y and z. And then in the second equation, I'm going to integrate both sides with respect to y, and that's going to give me that f has to be xy squared plus y e to the z plus, I'm thinking of both x and z as constant, so I could have any function of x and z here. And then lastly, I would get this. And all 3 of these, so I have 3 possibilities for f, but these all must be equal because I'm just finding one function f. So looking at all 3, the only way all 3 can be equal is if c1 of y and z is y e to the z plus any constant. C2 of x and z is just going to be a constant. And then C3 of x and y would be xy squared plus a constant. So again, that just comes from the fact that all 3 of those equations above have to be equal. So that's the only way that we can solve for C1, C2, and C3 and get one answer for f. So at the end, that tells me that f, my potential, is just going to be xy squared plus y e to the z plus a constant. And so this is a square, not a z. And what you should always do once you find your potential is just check by taking the gradient. So take the gradient in your head here and just double check that we do in fact get our vector field capital F. Okay, now if you didn't see it this way, I am going to show you another method in a second. But first let's finish the problem now that we have our potential. Okay, so from our work on the previous page, we found this potential function to be xy squared plus y e to the z plus a constant. So that means that the total work is just going to be that evaluated at 1, 2, 3, my end point, minus that evaluated at my starting point, just from the fundamental theorem of line integrals. And so we can see when we plug that in, I'm just going to get 1 times 2 squared plus 2e to the 3 plus a constant minus, I'm plugging in 0 now, so now I'm just getting 0 plus 1 plus a constant. And that's going to give me 3 plus 2e cubed. And so that's the total work done. Now, if you'd like to see the potential found using method 2 that I showed in class, then I'll show that on the next slide. Okay, so in this method, I'm going to line up our three equations all horizontally like this, and we're going to start with the first one on the left, similar to what we did in the merge method, where we're just going to solve this by integrating both sides with respect to x, thinking of y and z as a constant. So we're getting xy squared plus c1 of y and z, because I'm thinking of y and z as constants. Okay, now I'm going to take the derivative of this, what I got above here, with respect to y now. So the partial derivative of this with respect to y is going to have to be 2xy plus the partial derivative of c1 with respect to y. Okay, and I don't know what c1 is, but I'm going to use this equation now to help me get this, because I know that this has to equal 2xy plus e to the z. And so this tells me that the partial derivative of c1 with respect to y has got to be e to the z in order for those two things to be, in order for this equation to equal this equation. And that tells me that c1, which is a function of both y and z, integrate both sides with respect to y, I get y e to the z. When I'm integrating both sides with respect to y, I'm still thinking of z as potentially a constant. So now I'm going to have some new function that's just of z. So I'm going to call it h of z. So it's any function of z here. And this tells me that f, my f that I had up above right here, has got to be xy squared plus y e to the z plus potentially some function of z, so plus h of z. Okay, but I haven't used this last equation up here, if you've noticed. So what we're going to do is now take the derivative of this, take the partial derivative with respect to z, partial of f with respect to z, and that's going to give me y e to the z plus h prime of z. And now we're going to pull this down, and we know that this has to equal y e to the z. Okay, and we're going to use that to solve for h prime of z. This is going to tell us that h prime of z has to be 0. Which means that h is just going to have to be a constant. H of z should be a z, is just going to be a constant. So putting this all together, this means that f, so I just found that h of z is a constant. Up above I had that f had to have this form. So this means that overall my potential function is xy squared plus y e to the z plus a constant. And that's the same thing we got when we did it the first method. Okay, so again, either way you choose to find the potential function, at the end, just check. We take the gradient of this potential, we do in fact get back our vector field f we had up above here. And so then this is the potential that we'll use in our line integral. We'll apply the fundamental theorem of line integrals, and again we'll get 3 plus 2e cubed for the total work done. Okay, so I'm going to follow up with one more way to see why this vector field is conservative. You can either find a potential function like we did, and then you know it's conservative, or you can test to see what the curl of the vector field is. This is how we define the curl of a vector field. This is operator notation. You're going to look at, just like you did with cross products back in Math 13, we're going to think of a cross product type thing here. But instead of having vectors, we're actually going to use this operator. So as you recall, we've seen this before. This del operator we saw when we found the gradient. And it is really a vector. You can think of it as like a vector of these partial derivatives. But notice I didn't put any function inside here because I'm just thinking of it as an actual operator. So this notation doesn't even make sense until it actually acts on some type of function or vector field. So the way it's going to act on that is you're going to write the components, the m, the n, and the p, down here. And then we're going to pretend as if we were taking a cross product. So if you recall, if you take a cross product, you're going to block off the row and column that contain I. Then you're going to start here. And it's as if you're multiplying these two. You can't really multiply them, but you can apply that partial derivative to p. So you're going to have the partial derivative of p with respect to y, and then minus the partial of n with respect to z. And then you're going to do this for j and k, and you alternate signs as you go along while you're taking the determinant. So then your j component will be the partial of p with respect to x. So I'm blocking off the row and column that contain j. So I'm blocking off this row, this column, and then I'm left with this times this, which is, again, I'm not multiplying them, I'm applying them. So the partial derivative of p with respect to x minus the partial of m with respect to z. And then we'll do the same thing for our k. So in the k row, you're going to block off this top row in this column. And we'll now take the partial of n with respect to x, partial of n, minus the partial of m with respect to y. Okay, so this gives us a vector, and the components are defined by these difference in partial derivatives. And it is the case, and we're going to prove this at the end of the quarter, it is the case that if the curl is 0, then the vector field's conservative. And actually it is an if and only if. So if you have a conservative vector field, then you also know that the curl will be 0. So you can try this now with our actual function. Just replace m, n, and p with the actual functions we had. So let me do that. Okay, so if we want to see the curl of this particular vector field, we'll start with the I component. So I'm going to take the partial of this with respect to y, so that's just going to be e to the z, minus, then I'm going to take the partial of this with respect to z, so that's just e to the z. So I get that my I component is 0. And we're going to do j and k. Just for the sake of space, I'm just going to put it down below. So my j component, I'm going to take the partial derivative of this one with respect to x, that's just 0, minus, I'm going to take this one to here, minus the partial derivative of that one with respect to z, so that's also 0. And then we'll do our k component, so that's going to be taking the partial derivative of this with respect to x, which is just going to be 2y, and then we will take the partial derivative of y squared with respect to y, which is also 2y. So if you notice, using the curl, we get the curl is the 0 vector, which means that this vector field is in fact conservative.